Okay, so today is Friday, TGIF. It's Friday, November 13, and we're making it through the semester. Let me see. There's one more week after this, and then we have Thanksgiving break, correct?
Yeah.
And so we'll see if Purdue is. It's like Purdue's got the football. We're running towards the goal line. The COVID defender is trying to tackle us, and we're like, the question is, are we going to get the ball over the plane or not? You know, or are they going to tackle us on the 1 yard line? I think we'll get the ball over the plane probably, but it might not be pretty. In any case, today we're doing Markov chains. So we're going to start Markov chains, which are really interesting. So we're going to do Markov chains, and then we're going to do hidden Markov models, because hidden Markov models are essentially an application of Markov chains, which is very analogous to what we've done so far with Markov random fields. Okay, so Markov random field, and then we have some sort of observation. The observation is like y equals ax plus noise, right? You know what that means now, right? If I had said that at the beginning of the semester, you'd be like, what's he talking about? So you have learned something, right? So feel good about that. So y equals ax plus noise, okay? So the y is the observation. X is the unobserved quantity, right? And then x we often model with like something like a Markov random field, right? Well, it's the same idea with hidden Markov models. Hidden Markov models actually came first, but it's a 1D model instead of 2D, or multidimensional. And instead of it being a Markov random field, it's a Markov chain. Now the beauty of this is that for the Markov chain case, you can calculate exact quantities, okay? So it's not like you just have to do this coordinate descent thing and maybe converge to a local minimum. For the Markov chain case, it's actually discrete, so it's not even convex. It can't be convex because convexity requires that you be on a convex, your domain be a convex set. And the discrete domain can never be convex, because if you take averages of two lattice points, you fall in the middle like no man's land. It's not a place, right, on the grid. So you can't, convex optimization doesn't work. But you can get an exact solution in the 1D case, amazingly enough. And there's algorithms for doing that. They're based upon dynamic programming, if you've heard of dynamic programming. So dynamic programming, sometimes called the Viterbi algorithm, or sometimes it's called the Bell's algorithm, or it's sort of a general method for solving problems. And in the particular case of the 1D problem, it turns out to be polynomial complexity. So it takes what you might think would be an exponential complexity problem and makes it polynomial complexity, which is nice. And the algorithm for doing that, you still use the EM algorithm, so it's still iterative. So, okay, it's still iterative. So in that sense, it's not closed form. But what's closed form is the computation of the Q function. Remember the Q function we've been talking about? The Q function is the thing we replace the log likelihood with. So you have to do a maximization of the Q function, right? Well, the problems we looked at, the Q function was easy to maximize. There were clustering problems, so that was easy. But for some of these problems, it could be hard. Like if you have map estimation, non-convex prior, computing the map estimate is hard because it's a non-convex optimization problem. So the Q function could be hard for problems like that. But it turns out that for the special case of hidden Markov models, it's polynomial complexity. So that's an important special case to understand, because it, you know, if you have like a problem which is kind of generally exponential complexity, or not, it's not really, okay, it's what's called NP hard, non-probabilistic, well, it's just non-probabilistic. It means it's non-probabilistic polynomial. Okay, what it means is that if you have an oracle to tell you information that you don't have available, you can solve it in polynomial. Well, okay, what it really means is that, well, it means two things. You should take the course on computational complexity so you'd actually know what it means. I think Professor Kack teaches that in ECE. Excuse me?
Professor Bob Givan, 608.
Oh, okay. Who is that again?
Given.
Oh, Givens, yeah. Okay, but I thought Kack also teaches a course like that too. But anyway, yes, so that's good, okay? But the summary is that all NP hard problems are supposed to be equivalent, okay, in complexity. And basically, they all map to something like the traveling salesman problem, which is exponential complexity. I'm lying slightly because it isn't necessarily exponential complexity. It's just that nobody's ever been able to prove that it isn't, okay? So it's assumed to be exponential complexity. I mean, it is possible someone should someday prove that it's polynomial, although I wouldn't hold my breath, okay? And then that would have a lot of interesting ramifications. But so the short version is it's exponential complexity. So in normal problems, they're exponential complexity. So if you find one that turns out to be polynomial, that's interesting. Okay? And actually, there's another one I'll just mention is polynomial, which is kind of, there's this thing called the Ford-Fulkerson algorithm. Are people familiar with that? The min-cut max flow, or max-cut min flow, or something like that problem, which is the other sort of notable special case, which is polynomial complexity in 2D. So we'll talk about the hidden Markov model, okay? But actually, the Markov chains are mostly, well, they're interesting because of hidden Markov models. That's sort of an application, you might say. But more generally, Markov chains are interesting because they're like differential equations almost, okay? That differential equations have, like, you know, a particular solution and a general solution, and they have, you know, different kinds of properties. And Markov chains are like that. You can find like stable solutions to them, okay? And that's called when they're ergodic, okay? Which is sort of a circular thing. I mean, it's ergodic if it has a stable solution, okay? So it's really semantic in that sense. But but finding the ergodic solutions of Markov chains is interesting because it's like solving a differential equation or something. It's often the solution of some problem you want to know, okay? And in general, getting the ergodic solutions of Markov chains is hard. And but there's a lot of but sometimes it's easy, okay? And so we're going to talk about that. And it's a really important concept because it also plays a key role in something else which is becoming more and more important these days, which is, I don't know, maybe what you might call probabilistic algorithms. Things like stochastic processing, Markov Monte Carlo, Markov chain, MCMC, right? Monte Carlo Markov chain methods. What is it? Markov chain. Monte Carlo. Okay, thanks. Markov chain Monte Carlo methods. Okay. So we know what a Markov chain is. Do you know what Monte Carlo is? It's a city in Europe, right, where they had gambling. So it doesn't have any deep technical meaning. It just means that you're like rolling the dice, as you might say. So you can use these methods to do simulations of systems, real physical systems. So you might have some complicated system, and you'd like to know something about its behavior. So in order to be able to know something about its behavior, you have to model it, and you might want to do a computer simulation. But the simulation depends upon things like random events. So then this question of how you generate samples from the distribution of some random process that corresponds maybe to a physical system is important. So that's these Monte Carlo Markov chain things. So typically what will end up happening, we'll see that if you want to generate random variables from distributions that are complicated, then it turns out one of the best ways to do it often is that you generate a Markov chain. And the underlying concept of a Markov chain is that each new random event depends on the previous random events. So it's like a sequence of random events that produce some kind of outcome. So understanding the asymptotic distributions of these things is important because it'll tell you a lot about how you can do those kinds of experiments. We'll talk about a thing called the Metropolis algorithm. And the Metropolis algorithm is sort of the most classic method for sampling from distributions with Markov chains. And I guess Metropolis was a chemist, I think. Okay, so they came up with this idea, and then because they were trying to do computational chemistry, so they wanted to simulate the behavior of some chemical system. And then it turns out there's some constraints on the Metropolis algorithm that make it hard to use sometimes. It's like, so then we'll talk about a thing called the Hastings Metropolis algorithm, which is sort of a more general version, which applies to a wider range of cases. And the other thing we'll talk about is reversibility. So it turns out that Markov chains are, in general, it's often hard to find their ergodic distributions or their stable distributions. But if the Markov chain is reversible, it turns out it's really easy to find those solutions. Okay, so then the trick becomes when are Markov chains reversible? How can you make them reversible? How can you construct them to be reversible? So that's kind of like a 40,000-foot view of what we're going to do in maybe the next week or so. All right. So let me talk about what a Markov chain is. Okay, so the idea is you have Markov chain. Markov chain, the word, so whenever something's Markov, it means that the next sample is dependent on the previous sample. If you say it's a chain, that usually implies that the state and the there's a sort of an input and an output, right? The input is like what you might call the independent variable. The independent variable is time. They call it the independent variable because you can set time to whatever value you want, right? And then the dependent variable, or the state, is the value at that time, right? So either the independent or variable or the dependent variable can be continuous or discrete, okay? So if you say Markov chain, it usually means that the state and the independent and dependent variable are discrete. They're both discrete. So it's discrete in time and it's discrete in state. Okay, that's the easiest case to handle mathematically. But maybe we'll touch on some of the other cases. I mean, most of what I say for this case will more or less kind of be true. And the if the state is continuous, that's usually a fairly direct extension. But if the time is continuous, then things get complicated. It's actually interesting. I shouldn't get into a tangent, but if the time variable is continuous, then things get really messed up, okay? If you enjoy reading about very messed up mathematical systems, then you should totally get into that, okay? Because it turns out that actually even to do anything, and when the state becomes continuous, it breaks everything. Like there's a thing called Ito calculus, and it turns out that you have integrals. The integrals are different, okay? So the integral of x dx, normally the integral of x dx is x squared, right? It's not. So normal calculus breaks when you go to that situation, which is kind of weird. But so we won't deal with that. So we'll just deal with the case where the state and the time are discrete. So in that case, and sometimes we'll make the state continuous. You know, I'll like kind of do this a little bit. You won't notice too much, and we'll kind of go with it because it's almost the same. So, so what will happen is that you have xn, okay, where xn is a random variable, but it takes values in 0 through, say, n minus 1, right? And then n takes values, we'll usually start at 0 through infinity, kind of a thing like that, right? And then the probability of xn equals, say, xn. This is an uppercase x. That's the random variable, and this is its value. Actually, what I'll do is I'll make this j. Given xn minus 1 equals I, okay? Or given xn and then say, I guess I'll make this I1, and then xn minus 2 equals I2 through x0 equals I guess this would be like n minus 1, something like that. That's equal to the probability of xn equals j given xn minus 1 equals I. I'll just make this I, so I can make that I. Does that make sense? So in other words, the conditional distribution of a state, given all the previous states, is only dependent on the past one. So the way we draw that, we have, this is x0, this is x1, this is x2, this is x3, and so on, okay? So what isn't true is that there isn't a communication channel like that. That's not there. I'll erase it. So everything x3 knows about the past, it knows about it through x2. So the way we say that is we say that x3 is conditionally independent of the past given x2, right? If I take this sample out, it breaks the chain. Okay. So if that's true, then it's a Markov chain. That's the defining property of the Markov chain, that each new sample is conditionally independent of the past given the previous state. Okay? Now, so this thing, okay, so I can define this thing then to be P, I'll put N, I'll put that in parentheses, IJ. No. Yeah, IJ, that's correct. Now, for some reason that boggles my mind, in the beginning of time, when they decided to define the notation, they decided that that if this is a matrix, that it would be IJ. So if the matrix looks like this is Pn, then this index is I, and that index is j. Now that was a particularly bizarre choice because, well, first of all, it's really super annoying because if you multiply a probability distribution, you always write this condition on that, right? And then you put the over thing here, so you multiply on the right, okay? But here, you have to multiply on the left, which is particularly bizarre because in every other convention with matrices, you always multiply the matrix on the right. So why they decided to switch it now? It was like they came along and they said, oh, look, we're lucky. It works out the right way, so it's not confusing. They said, oh, we'll have to change that to make sure it's still confusing for people. So they decided to flip it. You see what I'm saying? So what will happen is if you define P0, say, of n is equal to the probability that x0 is equal to n, right? No, I got this all mixed up. Yeah, no, that's right. I got it right. I'll make this I, because I think the n will cause confusion. Okay? So then, if you want the probability that x1 is equal to j, right? Then that, we would write that as the notation pi j1, correct? I mean, this is just how I'm defining the notation. And then we'd say that that's equal to this. Now, using conditional probability, we'd write the probability that x1 equals j given x 0 equals I times the probability that x0 equals I, right? And then you'd sum this. You'd sum this from I equals 0 to n minus 1, and that would be the correct value, right? Does everybody agree with that? This is just the standard definition of conditional probability and summing over the marginal, right? Now, so that actually, if I write it out in this notation, I get that this is P0 ij. Again, just to make it confusing, I have to put the P0 here, I, and I sum over I. So that's equal to pi 1 of j. So that's got to be true. Now, we say that homogeneous Markov chain, okay, what does that mean? It's homogeneous means that Pn ij equals Pij. So these are called transition probabilities. This chalk is terrible. Yeah?
For the expression for pi 1j in the sum, should it the p, should it be 1 instead of 0 right there?
No, I don't think. Hold on, let me just double check my own notation. Oh, you're right. So it's in my notes, I indexed it from the, did I do this right? Yeah, because this is n. Yes, that's correct. Thank you. And the reason I got that wrong too is because I almost never use that notation. Because the first thing you do with Markov chains is you usually assume they're homogeneous. That's like assuming a system is time invariant. So So you're assuming that the transition probabilities are not a function of time. So now, if the Markov chain is homogeneous, is it stationary? What does stationary mean, by the way?
Distribution or the
Distribution is not a function.
The distributions are not a function of time. And not just the distribution for each random variable in the sequence, but also windows of the random variables. So if you have a sliding window. So, but a necessary, not sufficient condition, but a necessary condition is that the distribution, that the pi's are not a function of time, right? Because the pi's are the marginal distribution of individual samples, right? So they should not be a function of time. So if these are a function of time, it can't be stationary, right? Okay, so the question is, well, if it's homogeneous, are they a function of time? Well, let's see. If I define pi, say n, to be equal to, this is pi n, say 0 through pi n minus 1. That's just the vector of probabilities. So this is just a probability vector that describes the probability distribution of the m-dimensional thing, okay? Okay, so what does that mean? It means that you got like m classes. So you have, say, 10 classes. This is a 10-dimensional vector of non-negative values that sum to 1 to tell you the probability that you're going to be in each of the 10 states, okay? Is everybody clear what this is? Okay. So then what happens is that pi 1 is equal to pi 0 times p. What's p? Oh, p, I'll write it here, it's a little sloppy. P is what? It's Pij, it's the matrix, right? So the vector matrix multiplication is exactly the sum. So that's good, right? Now, pi 2 is equal to pi 1 times p, right? Because it's the same deal. Does everybody see that? So it's pretty clear that pi n is equal to pi 0 times p to the n. There's no parentheses there. Because I just keep multiplying by p. Every time I multiply by p, p is a matrix. Every time I multiply by p, it's like click, I take one step forward, right? So the distribution at time n is that the distribution at time 0 times p to the n. Yeah?
The pi is not the row vector as in the column vector?
Ah, yes. Thank you so much. That was the thing I was complaining about, too.
Yeah.
My brain automatically reverted. Thank you. Yeah, I mean, it's really annoying. But it's the way everybody does it, so it's a little too weird if you flip it. It's a pretty widely, of course, I need to get the deep learning people involved in this field, because they'll change all the notation with impunity, and then the entire world will have to change. So, okay, so, but this isn't the actual random variable. This is just the distribution of the random variable, right? So you got to keep that straight. There's a difference between the random variable itself and its distribution. Now, the question I was asking, is this homogeneous necessarily? Well, I can set pi 0 to anything I want. Let's say I set it to 1, 0, 0. What does that mean? What does it mean if I set pi 0 to that?
Probability of finding class 0 is 1.
Excuse me, say it a little louder.
Probability of finding class 0 is 1.
Initialize the
Well, what does that mean in sort of, that's correct, but what does that mean in sort of plain language?
You've initialized the Markov chain at state 0 with some time.
You've initialized the Markov chain into state 0, right? Because with probability 1, it starts in state 0, correct? Now, then pi 1 is equal to pi 0 times p, right? Does this have to be equal to pi 0? Not necessarily. I mean, it depends on what p is. So actually, let's talk about what p is. So what's p? So p is a matrix, right? And this is I, and that's j, right? And this is Pij. Pij is the probability that if I start in state I, I go to state j. Right? So a row, this first row, say, the first row, row 0. By the way, in order to not drive ourselves insane, I'm going to, when I index matrices, I'll start them at 0, okay? Even though I know it's more conventional to start at 1. But that's really just because Fortran started at 1. And then MATLAB inherited it from Fortran. And now, I don't know. But now we got Python, so we can start all our indexing as 0, okay? So this is 0, right? And what does this row represent?
The probability that it'll transition into state J from state 0.
Yes. So this represents the probability that you started in state 0 and that you go to some other state, right? So what can you tell me about the numbers along this row? Tell me anything interesting about the numbers in the row. Excuse me?
They sum to 1.
They sum to 1. Why?
Because it's a probability.
Could- Yeah, it's a probability distribution on the set of output states given that the input state is 0, right? What else can you tell me about them? Something simple. They sum to 1 and something else. They're non-negative, right? So the sum over j of Pij equals 1, and Pij is greater than or equal to 0. Those are the two constraints. Any matrix which obeys those constraints is a legitimate transition probability matrix, right? So my point is this. If pi 0 is this, does pi 1 have to be equal to pi 0? No, because I could pick, I mean, it could, because I could say, well, this vector could be 1 and all zeros, which would mean that if I start in state 0, I have to stay in state 0. But it can change, right? And if it changes, then the probability distribution at time 1 is not the same as time 0. But this is a homogeneous Markov chain, right? Is it stationary? No. So the interesting thing is that homogeneous does not imply stationary. Just because it's homogeneous doesn't mean it's stationary. Okay, now, there are two different philosophies of the world Okay? One of the philosophies is held by electrical engineers, and the other philosophy is held by computer scientists. Okay? Electrical engineers believe that if you take any system and you run it long enough, it reaches steady state. Okay? And computer scientists believe that if you run any system long enough, it terminates. Okay? Which is a type of steady state, I guess. But electrical engineers really think that it goes like this. Okay? If you wait long enough, eventually any system will eventually go like this. Okay? Because I mean, they believe this. It's like a deeply held internal bias. Okay? Because all systems that they've ever dealt with, if you wait, I mean, if it wasn't for that, you wouldn't have oscilloscopes, right? The whole concept of an oscilloscope. I remember when I was an undergraduate and they first told me about an oscilloscope. I'm like, I don't get it. Like, especially in those days, you didn't have computers that could like store a signal, right? You'd be like, what am I looking at? Well, they were like, it's repeating. And you're like, well, why is it repeating? Well, it's repeating because electrical engineers think all systems eventually reach steady state. They all, you know, you put a signal in, it goes like, eventually it just kind of like does that, right? But computer scientists think that you run a program and then it gets to the end and it terminates. So computer scientists believe that Markov chains always like never reach steady state. Okay, so are transient. Okay, and electrical engineers think that they're reach steady state. Both things can happen, but reaching steady state is sort of has a lot of interesting consequences. Okay, and by the way, in computer science, this would be a finite autonoma, or probabilistic finite autonoma. Okay, so the point is this. So the question is, so you have pi n is equal to pi 0 times p to the n, right? This is the distribution at time n. This is so important, I feel like I should start. You know what I'm going to do? I'm going to erase this. Okay, fine. We made that point. I'm going to write it up here because it's super important. At time n, xn is equal to x0 times p to the n, right? Okay? So the question, oh, gosh. I hope that you guys saw what I meant to say rather than saw what I wrote. You should always hear what I mean rather than what I say. Okay, that's the distribution, right? So then, question is, does make this nice. Does the Markov chain reach steady state? Okay? So if it reaches a steady state, what that would mean is that in the limit, as n goes to infinity, of pi of n equals something. Does that limit exist? Excuse me?
Depends on your p.
It depends on p. It totally depends on p, right? So the limit, so that's equal to the limit as n goes to infinity of p to the n. Right? Well, the answer could be complicated. The answer could be complicated. But I can say this, and we will talk about the answer. Okay. Okay. So first of all, if for all pi 0, the limit as n goes to infinity of pi 0 times p to the n equals pi infinity. So if that's true, okay, then, well, okay. If I do this, right, this is a finite set of operations because I'm assuming that m here is finite. Okay, so it's easy to prove rigorously that that must be equal to this. Oh, okay. Let me write it like this. Okay, pi infinity is equal to the limit as n goes to infinity of pi 0 times p to the n, okay? But that's equal to pi 0 times the limit as n goes to infinity of p to the n. I can exchange this sum and this limit. It's always true because it's a finite sum. So when a limit is finite, you can exchange it with the sum, okay? You can prove that. Okay, so, and then this thing has to equal to, so if that limit exists, then whatever it is, it's something. And that something we call p infinity. Right, or I'll just make it like this. P infinity, okay? If that holds, then we say that the Markov chain is ergodic with stationary distribution what? P of pi of infinity. Okay? Now, okay. Maybe I should pause here a moment and just make sure everybody's on board. Okay? So P is the transition probability, right? Okay? And the limit as n goes to infinity of p to the n, if it exists, it doesn't necessarily exist, we say it's p infinity. Okay? And furthermore, we have that, so this is 1, this is 2, and then 3. And then for all pi 0 times p infinity is equal to pi infinity. Now okay, does this make sense? Do you have any questions? I mean, we've kind of done a lot of small things, but sometimes they gang up on you and it can get confusing, okay? So everybody's got this all in their head. Now, think about this equation here. So we're saying we have a matrix, so we have a vector, it looks like this. Then we have a matrix that looks like this, okay? And then this thing is equal to this other thing here. Okay, and this is pi infinity. Yeah, I guess I'm putting that in parentheses for some reason. I don't know. Okay. Okay. Now, no matter how we pick this vector, oh, okay, can this vector be anything? First of all, this is an m-dimensional vector, right? Can it be anything? What are the constraints on it? It can't be anything, huh?
The values in it have to sum to 1, have to sum to
Yeah, so it would be non-negative and they have to sum to 1 because it's a probability density, right? Now, I'm saying no matter how I pick this, I always get the same thing. So what does that tell me about P infinity? No matter how I pick this vector, I always get the same thing. So, okay, let me pick this vector to be 1, 0, 0, 0, 0, like that, right? All zeros. Then what does that tell me about P? So this is 1. These are all zeros, except for the first one.
the first row of P has to be equal to pi infinity.
Yeah, it tells you that the first row is P infinity, right? Now, what about the second row?
All of those have to be pi infinity.
Right, because I could put this 0 and 1, okay, and then the second row has to be in P infinity, right? Where is this going?
All of those have to be pi infinity.
All the rows are P infinity, are pi infinity. So if this P infinity exists, every row is the same. Okay? Okay, so that's what it is, okay? Because what it's saying is, regardless of what state you start in, if you run the Markov chain long enough, eventually the distribution of the states will be the same. You know, it's a little bit like if I have a container of, you know, I mean, like, let's say, okay, I'm coming up with a stupid physical analogy. Let's say I have like some kind of like a gas container. Okay, so it's sealed, okay, and it has like a partition here, and I pour water here, and I pour gasoline there, okay? This is like a container that doesn't exist. You can't buy it in the store. And then you take this container and you shake it, okay? If you shake it, what happens eventually? The gasoline and the, okay, well, maybe I shouldn't use gasoline and oil. I'm not a chemist, I'm sorry. I should have used gasoline and oil, okay? What happens if you shake it? Because they're both polar, gasoline and oil, right? Oh, no, they're both non-polar, something like that. If you shake it long enough, what happens? They mix together, right? So the entropy goes to a maximum, and they mix together, right? So that's just a Markov chain. So if you shake it, like with each shake is a step in the Markov chain, right? Eventually, asymptotically, it reaches a limit. It doesn't matter. You can start with the gasoline here and the oil there, or the oil here, or the oil here and the gasoline there. It doesn't matter. Asymptotically, it gets to the same answer. So that's what's happening here. The idea is that for some p's, eventually, you'll reach an asymptotic distribution where it won't matter what the initial state was, because it just gets all shook up, okay? All right, do you have a question?
I'm not convinced that we can put everything in pi 0, that we can plug any vector in pi 0, unless it is a problem.
I'm sorry, it's a little hard to hear because you know, the room's a little noisy, and with these masks, it gets a little tough.
I'm not convinced that you can plug in any pi 0.
It's definitely the case that there are Markov chains which don't meet this. Definitely. So I'm not telling you it's always true.
Yeah. But even with all these conditions,
Well, I have put no conditions down. These are assumptions. So your concern is completely valid. I agree with you. I'm not disagreeing with you. I'm not saying that this is true. I'm saying if it's true, okay? So I want to be real clear about that. You're correct. We're in agreement. Your concern is that maybe this might not work. And the answer is yes, that's correct. Sometimes it doesn't work. I'm going to talk about it. But sometimes it does work. When it does work, we say the thing's ergodic. So right now, it might be that the set of ergodic Markov chains is empty. Maybe it never works, okay? Maybe it always works. Maybe it works sometimes. As you might expect, it works sometimes, okay? But it doesn't always work, so your concerns are valid, all right? You're absolutely correct.
but you said making conclusions about T infinity.
Okay, now that is prefaced on the assumption that the P infinity exists.
Yes, but
So if the limit does exist, okay, so from a mathematical point of view, I have a matrix P, right? You know how to multiply matrices together, correct? So I can multiply the matrices together n times, right? So that sequence you get while you multiply them together, each entry in the matrix forms a sequence in time, right? N. That sequence can either converge or not converge, right? So any time sequence n is either, from the definition in calculus, it's either convergent or not. There's some sequences that don't converge and have like cluster points or have a convergent subsequence. You know, there's all those kinds of things. But in general, a sequence either converges or it doesn't converge. So by saying that this exists, I mean that every entry converges. If that happens, then this has to be true. Well, you're right. There is like one little glitch I'm not quite showing, which is that, no, actually I did the whole thing. I'm good. Okay, there's one other thing which I have to show that I'm going to just appeal to your sensibility. That if I multiply this, I get this, right? Certainly, if I multiply on the left, it's got to be true, right? Because that's the same is equivalent to this. If I multiply on the right, it's also true, but I don't know. That just, I mean, if there's any justice in the world at all, if you multiply by something an infinite number of times, and then you multiply by one more time, it's got to still be the same thing. Okay? But other than that, it's a rigorous proof, I believe. Okay? And that's not too hard to show. Okay. All right. Good. So the idea here is that, like, when does this converge? Okay. Now, what I'm going to do is, we're out of time. So I'm doing this a little bit out of order. The next time what I'll do is, in the notes, there's a simple example. Actually, I could just show it to you real fast because no one's coming in here anyway. Because maybe I'll skip it because it's not that complicated. It's easy for you to read. It's this simple example. This is a nice little example, just to give you a little intuition. So tau, okay, that tau j is just a shorthand notation for the probability distribution of the first state, okay? Oh. That's weird. Oh. I forgot to plug it in. There it goes. There we go. Okay, so tau 0, this is the probability distribution of the first state. There are two states, m is 2 in this case. So it's just saying you have a 50-50 chance of being in either of the first two states, okay? then the probability of being in the next state is that with probability rho, you change states. And with probability 1 minus rho, you remain in the same state. So for every step of the clock, you flip a coin, which has probability rho of coming up heads. And if it comes up heads, you change states, okay? Now, the intuition is usually that rho's small. So if rho is small, most of the time you stay in the same state. And then every once in a while, at a random time, you switch, okay? Okay. Then, okay, so that's what this looks like. So this is a simulation. So this is the case if rho is 1%, okay, it's 0.01. So most of the time you stay in the same state. On average, you stay in the same state for, I don't know, I kind of want to say 100, but that can't be right. It's, I don't know what it is. It's some number, you can calculate it. Maybe 50, okay? If you do queuing theory, you'd know this off the top of your head. And then you flip. But once in a while, you get a lucky or unlucky, and you flip faster than you expect. Okay? So that's what it looks like. Does that make sense? Now, if you make it 0.5, every time you flip with 50-50 chance, what that really means is it's independent from sample to sample, because it really doesn't matter what state you were in previously. Do you see that? It's intuitive, maybe. You could do the calculation to show it. But if you were in state 0 with probability 1, and at time 1, you'd be 50-50 chance of being in either state. So it doesn't matter what your previous state was. So in that case, they're IID, independent, identically distributed, and they're uniformly distributed between 0 and 1, right? But if rho is 0.9, then you flip almost all the time. Every other time, you always switch state. You almost always switch state. And what happens is that it's kind of a weird thing, because you go tick tock, tick tock, tick tock, tick tock, tick tock. You see what I'm saying? Every once in a while, the gears go click accidentally, okay? And it gets out of sequence. So you have this effect with a phase change. This comes up in material science, where you get this phase change. It's like the crystal slipped, right? So those are sort of, that gives you some basic intuition, a very simple Markov chain. Now here's the other thing that's true. If I want to estimate rho, how do I do that? Oh, well, maybe I will talk about that next time, but you keep track of two things. Well, okay, the first thing's silly. You just keep track of what the first state was, okay? So nj here is equals 0 or 1 for j equals 0, okay, or 1, right? This thing, Kij, keeps track of the number of times you go from state I to j. It's like it's a histogram on pairs. It's a histogram, but it's on pairs. It's not on single ones, it's pairs, right? So if there's any justice in the world, and if you hadn't taken this course, you would just say, oh, what's the maximum likelihood estimator? Oh, you go through a lot of calculations, blah, 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 blah. The maximum likelihood estimator of the probability distribution is that you take this Kij, you just normalize it so that, so that you have to normalize it so that j sums to 1. Because remember, in Pij, the sum over j has to be 1. So Pij can't equal Kij. You have to normalize it first in order for it to be equal. But otherwise, it's just like counting the number of people who like vanilla ice cream, okay? If you want to, it's the same thing, only it's on pairs. So that's the maximum likely estimate. We'll need that later, because when we do the EM algorithm, we want to calculate the probability distribution. We want to estimate the parameters of the Markov chain. You'll need that, okay? All right, and then the next time, so that's good, and I'll hit off or mute. So that's good, and next time what I'll do is I'll get into, I'll review some of this again. Maybe we'll talk a little bit more about the asymptotic distribution of the Markov chains, because that's really cool. So I'm doing this in reverse order. And then I'll talk a little bit about Markov models and the EM algorithm, which is, this is how the EM algorithm was originally called the Baum-Welch algorithm. It was developed specifically for estimating parameters of Markov models. So it's the classic application of the EM algorithm. All right, have a nice weekend. Thanks, bye.